Okay, welcome back for Beginning Bioinformatics Part 6. This is the last of our Beginning Bioinformatics tutorials. If you haven't already done it, get the document from Canvas to go along with this tutorial. This last part is all about expanding our Python toolkit. Today we're going to install and use a package called Biopython that doesn't come pre-installed in Anaconda. So Rosalind problems 7 through 9 are going to ask us to do some things with DNA or RNA sequence, like transcribe, translate, compute GC content. And we could, at this point, develop our own Python code to do those tasks. But it's way more efficient to use these external packages that are built into Biopython. So how do we get access to those packages? So let's go ahead and start up Anaconda Navigator. And you may remember back to, I think it was tutorial part 4 when we first installed Anaconda Navigator, that I showed the home screen, but then I also showed this environments tab. And this shows all of the packages that are installed in your current Anaconda environment. So for example, when we're coding in Spider, all of these packages are already available to us to use. Now, Biopython is not normally in that set of installed packages. So we are going to change over to list all of the packages, and you can see that now all of a sudden I see all of these packages that don't have green check marks. Only the green check marks are installed. And if I search in the search bar over here for Biopython, you can see on my environment it is actually already installed. Okay, but that's because I've done this in the past. For you, that's probably an open box. So if you check that, and let me go over to the document here. So you'll check that box and then click apply, and you should see a little status indicator start scrolling on the bottom. And it may take a few minutes, but what it's going to do is go online to a repository, get Biopython, and install it into your environment so that you'll have access to those packages. Now, if for some reason, when you search for Biopython, it doesn't show up, it may be because you don't have access to the right channels. So I already have a default channel, which is where it goes and searches for Python packages. But then there's also this one, CondaForge. And so I've given you instructions in the document here to add CondaForge. What you'll do is click Add, and then in this box, click this URL or paste in this URL. Easier said than done. Used it as a link, and actually there was a little delay there. It opened up multiple times, but in the CondaForge repository, that's what it actually linked to. This is just showing you all the packages in that repository. So you'll add this CondaForge repository. It'll go look, and it should add that. And then you click Update Channels, and ideally, whether or not you had to do that, you should get Biopython so that you can check that and then apply it, and then you'll get this sort of loading bar. Once Anaconda Navigator finishes all that, you should be able to start up Spider. spider started. And we should be able to go to the console here and say import bio. And nothing happened, which is a good thing in this case, because if bio was not installed, or if Biopython was not installed, this import bio would give us a module not found error. Since we didn't really tell it to do anything except import the module, since no errors popped up, that means it was able to import the module, and Biopython is installed. So this environment is what you should see if everything is going smoothly. A little bit of a detour here to test whether Biopython is also visible from your terminal. So if you open a terminal, and then we can go to an interactive Python shell here. So I type Python 3. Right, so we've done this in the past as well. Right, the 3 greater than sign tells me I'm in an interactive Python session. And I can do import bio here. And again, no errors. That means my terminal has Biopython installed and accessible. So no problems there. If you get a module not found error, that's what this whole section is about. So if you got a module not found error, then we need to exit out of here. Even if you didn't, if everything's working, you still probably want to exit from the interactive session there. But if you got a module not found error, there's going to be a couple extra steps here. So I give you the command to tell Conda in your terminal environment to go install Biopython from Conda Forge. So this command, I'm just going to copy paste it right out of the Word document. Says Conda, which if you remember back a couple modules ago or a couple tutorials ago, Conda is a package manager. So it's saying Conda install from -c is saying I'm going to specify a channel. So we're not going to use the default channel. We're actually going to use the Conda Forge channel. So from the Conda Forge channel, import and install Biopython. So if I click enter there, this may take a minute, pretty fast at the moment. So what it's doing is going online, looking in Conda Forge to see if there's a package called Biopython. Now it's looking in my environment and comparing it with what Biopython needs. And in this case, it says warning, there's a newer version of Conda, so I could update my package manager. I'm not going to do that. And then it gives me the package plan. So what is it going to do if I say yes? Well, it's going to install Biopython 1.8.1 from the Conda Forge repository. Okay, so I'm going to say no because I already have a functioning Biopython here. I don't need to install it again. Probably wouldn't hurt for me if I said yes, just overwrite it, but I don't want to do that. If you had a module not found, you don't have Biopython installed for your terminal, then click yes, and it will install for you. Okay, and if you click yes, you'll see progress. It will download and install Biopython, then go back and do Python 3, import bio, and see if it works. So you should get to a point where you can do import bio and then have no error message. If you still are getting errors, I give you one more link there to check. And then I just also installing external packages. If you do bioinformatics long enough, you're bound to run into dependency problems. I mentioned this at the very outset of learning Python. One of the great things about Python, there are lots of developers, there's lots of ways to extend it, lots of packages and functions out there, but it creates these dependencies that at some point code breaks. I give an example here one time that it's not even all the sort of Anaconda's dependencies fault. In this case, the Xcode tools on my Mac, which is a development software built into Mac, and it installed. I didn't even realize it had updated, but it updated my system's default Python version, and that broke all my Python code. And I didn't know that it had updated Xcode. All I knew is suddenly none of my Python would work. And it took me days to figure out what was going on. Very frustrating. All of that is just to say, it's inevitable. Dependency problems will happen. The solutions are Google, patience, and experience. Experience sort of teaches you to be patient and that you will find a solution. So that is all just sort of words of wisdom and experience. I don't know, maybe not wisdom, but experience for sure. All right, let's use it now. So why did we go to the trouble of installing Biopython? However much time that took, probably it's going to be recovered in the time savings we get from using the functions in Biopython. So the first exercise here is the Seq object. So we've dealt with file objects before. Now we're going to define a Seq object so that, sort of analogous when I first introduced the idea of Python being an object-oriented language, I made the analogy to defining a circle object and then knowing how to calculate the perimeter or the area of an object that is defined as a circle. In this case, we're going to define a sequence object, and then once Python knows that this is a sequence object, it's going to know how to do some certain functions on that kind of object. In our case, it'll know how to complement or reverse complement, transcribe, translate, all that good stuff. So let's start a new code bit here. So I'll go here. So the first line from bio.seq. So this is just like we've done before, where we say from this module import this function. This notation bio.seq is actually the way you specify a path to a specific module or function. In this case, Biopython has a subdirectory called seq that has the function seq in it. So it's a little confusing, but that would all be explained in the wiki on Biopython if you were having to learn this on your own. So we import this function seq, and now we're going to, the function seq defines a sequence object. So we define mySeq equals, and then we use this function to make this thing, make Python recognize that as a sequence object. The cool thing about that now is that we can say print, when we say my sequence, Python knows my sequence is a DNA or RNA sequence, and it then knows what to do when we tell it to do complement. Let me run this. And what you'll see is Python calculated the complement to that sequence, right? So G, the complement is C, A, the complement is T, and so on. So that's pretty cool, huh? We didn't have to write any code to do all that switching from G to C or A to T or any of that. We could also, right, we could tell it to do the reverse complement. So there, we got the complement, but it flipped it around. So we got the reverse complement of that sequence. We could transcribe it. So now what transcribe did was change all the T's to U's, right? So now it's transcribed from DNA to RNA. So let's now jump over to Rosalind, because Rosalind number 7 is actually to transcribe some DNA. So number 7. And what I've done already, what I've been showing you, is I copied this earlier. Into that. So I've already been using the number 7 sample data set. And so if you compare the output for my transcribe is already giving me the correct answer. So I'm pretty much ready to go. I can download the data set. And it's pretty long, but it's okay. Paste it in there. So now this Seq object has all of this long DNA string in there. And I'll run it again. And I'm just going to copy it out of my console, paste it in there. And I've got to save that. What is this, number 7? Wait, can't type. Ros 7. Okay. So I need to tell it my code and then submit. So super easy, all because we've imported Biopython. You can imagine if we had to write code, it wouldn't have been hard code to do, right? Because all we have to do is write something that says, if it's a G, make it a C. If it's a C, make it a G. Or if it's a T, in this case, if it's a T, make it a U. That's all we would have to do to transcribe. Okay. Not complicated tasks, but we didn't have to do any of that. We just told Biopython that we defined it as a sequence object, and then asked it to give us to transcribe our sequence. Very handy. Rosalind number 8 is to translate RNA into protein. So here, one of our commands is to translate. Now, I want to show you, let's go back to the tutorials. So I just went back to the Biopython tutorial and cookbook, and so this is just to show you if you were trying to learn or find out if Biopython has a function that you need. So have something new that you need to do with the DNA sequence. I'm just doing find translate. And so it'll jump down here. It says, OK, chapter 3 is about sequence objects. That's a good start because we're dealing with sequence objects. Let's go down. So translation, this is a section in the document that tells us, yes, there is a function translate, and there are a bunch of options. So apparently we can translate in all kinds of different like codon tables. We can use mitochondrial translation or you know, other translation tables. So one is the standard vertebrate mitochondria, so on. Okay, but the basic functionality is just the object dot translate. So let's change this to translate. So, and I'm going to save this as, oh, I didn't want to save it as 7. File, save as 8. Okay, so where's Rosalind? Here we go. So let's go to Rosalind problem number 8. And here I can see it gives us some RNA sequence. I'm going to paste that in there and should translate for me. Did it give us what Rosalind expects? Well, yes. Mama protein string asterisk. Well, the asterisk on the end might give us an error because it looks like, so what it has done is Biopython has translated the stop codon into an asterisk, but Rosalind doesn't have the stop codon printed at all. Let's go back. I already so here, this is the section that talks about what to do about stop codons and whether you want to translate them or not. So in this case, you see by default, if you don't tell it anything, it translates the stop codons into asterisks. This might be kind of small for you to see, so I'm going to blow it up. yeah, so here, right, if you don't give translate anything, you get the stop codons translated. If you tell it to stop equals true, see how it stopped translating at the first codon, first stop codon, and then it didn't print the asterisk. And in this case, we know that it's the standard translation table, just because our translation is matching what Rosalind already expects, except for that stop codon. So what we can do to make it not print that asterisk is say to stop equals true. Right, to stop equals true should stop translating whenever it sees the stop codon and not give us that asterisk. So I hit run again, and indeed we got no stop codon. So that looks exactly like what Python wants. Now, of course, the sort of quick and dirtier way would be when you get your output, just delete the asterisk. Okay, but this is the more appropriate, more universally, doing it this way will work all the time. Especially if you were gonna, you had this in a pipeline or something. So let's get the real data set. This is Rosalind Pro. So that's a big RNA sequence. Paste it in there. Run that. So this is our translated protein. Copy that. Paste it in. And submit. And so we got it right. Okay, so not too bad with Biopython. The built-in functions are now doing all the work instead of having to reinvent the wheel in some sense. So that's 7 and 8. BP3 is another new function called SeqIO. So this is a module with functions for reading and writing a bunch of different sequence file formats. So the one that we'll deal with first is fasta, but you could also download GenBank files, and it knows how to parse GenBank and some other as well. Right, so I give a link here to, if you want to learn more about the different formats that it can parse, they're all in that. You can find them in that link. And the sort of magic function in SeqIO is this parse function, and it works a little bit like the file open. So right, when we were doing with open and then file name and then mode, well, parse will take a file name and then the file type, and it will know how to read in that file, and given the file type, it will convert that, it will parse it into individual sequence records. So we're going to use parse in a for loop to put all of those sequence records and extract information from them. So let's get a new file going. And we need some practice data. So let's get the practice data from Rosalind problem 9, since that's where we're headed anyway. So copy that, paste it into a document. So here, got the practice data for Rosalind number 9. Okay. And we make sure that you save this. Save it as practice number 9. I'm going to put it in my downloads folder. So we've got our practice data. And now we need to import this function. So from SeqIO import parse. And then this is a standard for loop in some ways, right? The standard format for a for loop is for item in list or some iterable object. In this case, we can put the parse command right in there as the iterable object. So this is going to use parse to get one record at a time from this file. And it's going to be able to read that. We're going to tell it is a FASTA formatted file. Right? You can imagine how much coding this is saving us. Right, so just by telling the parse function that this is a FASTA file, it understands that this is going to be header line, sequence line, header line, sequence line, and so on. And if there are extra line breaks in there, it will know how to deal with them. Saving us a bunch of coding and potential headaches. And not only that, but if this, the file we wanted to parse was GenBank format, we could just type in GenBank there and it would know how to deal with that too. So really nice tool. So let's go ahead and write our for loop here. And right, so your path here to this is going to be slightly different than mine. Make sure that you're specifying the path to that practice file correctly. Otherwise, this will fail. It'll not be able to find that data. Okay. And then what do we want to do with the seq records? So first time through the loop, seq record is going to go and get something from that file. So I think the easiest way to learn this is just to look at output. So I'm going to fill in the rest of that script, just like it is here. And I've got the explanation here, but let's walk through how this looks. Okay, just ask for permission. And so let's look at my terminal here to see what happened. My console, I mean. So it ran this program. First thing it prints is the seq record ID. So it recognizes the ID, right? It's getting that from the header line in my FASTA file. Then it prints the seq record sequence. So it knows that that second line in the FASTA file is the sequence. Then there's a new function here that I haven't introduced before, len, so len, it's short for length. So it will return the length of whatever object is in the parentheses. So in this case, we've passed it the SeqRecord.Seq. So what this did, len of SeqRecord.Seq, is count how many items, right? It said how long is that sequence. Apparently it's 80 base pairs. Okay. And then the last thing is we said print SeqRecord. So what did it do? It printed the whole SeqRecord. So those next 5 lines were the actual sequence. Okay. And interesting, it kind of, for the Seq object, it actually printed it in shorthand. Condensed it. Okay. And this bit about line 9, what did it do? It actually recognizes the sequence, and then what this is saying is it's converting it to a sequence object. So why is that cool? Why am I highlighting that? It's because now the sequences in this file, we can use all of those functions that we had from Seq objects, right? So we could tell it to translate or transcribe any of those sequences, right? So we could do any kind of function we want to on a sequence object, or any kind of function that a sequence object can do. All right, so the last one here is computing GC content. So the GC function will compute GC content, but it's in yet another module within Biopython called SeqUtils. So it's a bunch of utilities for dealing with sequence. So let's just look at Python number 9. So this is going to be giving us at most 10 DNA strings in fasta format. So now we know how to deal with fasta format. And we want to return the ID of the string that has the highest GC content, followed by the GC content of that string. So, right, we want the ID and then whatever the GC content is. And GC content is just, it's the percent of G's and C's in that string. Okay. So I'm not going to erase that. We might use some of that. So I've given you some pseudocode to try to help get you started. And the task 4.1 says modify the script in BP 3.1 so that it prints the GC content for each sequence in the file. So we've already got parse in there, but we need to get the GC function in here. So we get that from SeqUtils, so bio.SeqUtils. 'SeqUtils. 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 'SeqU because it's in the Biopython directory. And we need to import the function GC. So next, how do we get... I'm going to comment out these lines. Let's think about how do we get the GC content for a sequence here. We want to print, or not print, but okay, so first of all, how do we reference the sequence for a seq record? Right. So if we did that, what will it do? It should print our sequences, just the sequences over and over, right? So let's try it. So yes, in fact, that gives us just the sequences, right? So it printed 3 sequences, and I think that is correct. So let me 1, 2, 3 sequences in our practice file. Just making sure we didn't lose any. Now, how do we get GC for that? Well, we can apply the GC function, right? So here this is the syntax for the GC function. You just say GC and then parentheses, and in the parentheses we put whatever the sequence is that we want to compute on. So we should be able to do something like this. Just put GC around each of those sequences, and now rather than printing the sequences themselves, it should just print the GC content. Okay, so that is 4.1. We just got it to print the GC content for each of the sequences in the file. Now, how do we get to the Rosalind problem where we need to figure out which is the highest one, and we need to be able to print the ID of that one and then the actual GC content for that one. So that's where I've given you a little bit of pseudocode where we need some kind of variable to hold on to whatever is the maximum GC content. So let's just initiate something called max GC. That's just the name, right? That's what we're going to call our variable to be the maximum GC. If we started at 0, we know that there will have to be something higher than 0. And we're going to write something down here that says, you know, if the current GC content that we calculate, so we don't want to print this anymore. We want to say something like if GC, whoops, if the GC of that seq record is greater than max GC, then we're going to do something, right? I don't need all this these extra returns here. Right, so this should, right, what does the computer see when it says GC SeqRecord.seq? It should be seeing the GC content, right? What we printed over here. So it sees a number there, and it's asking, is that greater than max GC? So the first time through, it's going to calculate a number. It should be greater than 0. So what do we want to happen if that happens? We want the max GC to equal this thing, right? Because that's the new GC. That's the new maximum GC. So let's pretend now, okay, what if first time through it's 53.75, okay? That's greater than 0, so now max GC will become 53, whoops. Max GC will become 53.75. On the next time through, it's going to calculate this for the next 53.57. Is that greater than max GC? No, so it will skip that. Next time through, 60.9, this again, this will be greater than, so that'll be true, and our max GC should become 60.9. So I'm going to now, let's just make sure we're on the right track here. It's always a good idea, right? Print max GC. And hopefully, if our logic is right here, it should print 60.919. And in fact, that is what happened. All right, so that part of our script is working. We can get the max GC. Now, we need to also get the record for that, right? Because it's not enough to just print the number. We need to print the name of the record that it came from. Whoops. Undo. So every time that we get into this, right, this loop, this section, this condition is true where we've got a new maximum GC, let's make a variable called max record ID. And okay, what is that going to be equal to? That's going to be equal to the seq record ID. Remember a couple minutes ago when we were using the functions of the seq objects. So back here, right, when we did SeqRecord.id, it printed just the header line. So, or just the ID of, right? It would give us just this bit. That was the output of SeqRecord.id. So now we can say the max record ID, whenever this is true, is going to be our seq record ID. And right, our code was working to get the right number. So in principle, whenever it's on that seq record to give us that number, it should work to give us the correct ID. And so now what we need to print is max record ID, and then a new line, and then actually, yeah, the max GC. So that should give us the record and then the max GC on the next line. Can't concatenate a float. So I gave it the plus sign. Commas ought to work. Actually, the plus sign there will work because these are both strings, right? The record ID is a string, and then a new line, and then the max GC. Max GC is a float, and it's saying it can't concatenate that. Okay. That's so First I had the slash the wrong way. I always get my slashes backwards. Now I've got this weird space at the beginning of the number. These kind of little formatting things are kind of a pain. We've seen in the past already one way to fix this. Right, I was kind of being lazy there. Right. So I should probably have written it that way to begin with. Right, use the new line separator, print both of those things with the new line separator. And yes, indeed, there we go. We've got it. The extra decimal places here don't matter, I don't think. Let's try it on Rosalind and find out. There's some bit about absolute error here that's kind of interesting. About rounding errors and computation. It's not going to affect these problems. It raises its head in some, I call them edge cases, but we're not going to worry about those right now. So I just downloaded the data. So it went away. Rosalind.GC.text. Now, I need to modify my code to read the correct file here. So we were working on practice 9. Now we need Rosalind_GC.text. I think that's the name, right? Rosalind_GC.txt. So it's got more sequences and they are a little longer than the practice, but we run that and if all went well, that's our output. Upload our, oops, I didn't save it, did I? Save this as ROS9. So my code is ROS9 and submit. And it is correct. Okay. So little taste of dealing with sequence manipulation and computing on sequences. Right, so, and this is the end of the beginning bioinformatics tutorial. So the end of module 1. The next module, module 2, we'll start putting a bunch of these coding tutorials that we've been going through learning Python to some more complex tasks. We're going to learn how to, we're going to learn how to find the origin of replication in DNA sequence. So we'll develop some algorithms to do that are going to require us to use some of these tools that we've been picking up. All right, I'll see you back here for module number 2.